Up to this point, we considered the special mathematical construction called the vector space. We learned that for a particular set to form a vector space, it must satisfy two conditions. First, the operation of multiplication of the set member by a scalar must be defined, and the result of this procedure must belong to the set. And second, we must define the operation called plus, which takes two set members, we call them vectors, and returns another vector. I did not mention yet that there are conditions for these two operations to be defined correctly. First, the multiplication of any vector by scalar 0 gives us always the same vector, which we will call the zero vector. Let's denote it as this 0 with the small arrow above it. The addition of this zero vector to any other vector A results in the same vector A. Second, the operation plus must be a linear operation, which means that if the both input vectors are multiplied by the same scalar, the resulting output vector is also multiplied by this scalar. Third, the operation plus must be commutative, which means the order of input vectors does not matter for the output. And the last, the operation plus must be transitive, which means that if we add up three vectors sequentially, it does not matter in which order we perform this operation. Good. Now it's time for us to learn one more operation, the inner or scalar product of two vectors. This operation takes two vectors and returns a scalar. Let's denote it like this, with a thick dot for now. Because of this very common notation, the inner product is often called a dot product. Here Latin letters denote vectors and Greek letters denote scalars. To be properly defined, the inner product must also satisfy three conditions. First is called the conjugate symmetry, which means that order of the input vectors does matter for this operation. If we change this order, the result of the operation is conjugated. The second condition is linearity in the second argument, and the third is the positive definiteness, which means that for any non-zero vector x, the inner product of x by x is greater than 0. You can note that since the inner product of x by itself equals its conjugate, because of the conjugate symmetry, this value is always a real value. So we can rightfully place this last demand of it to be greater than 0. And if we have this operation defined in our vector space, then this vector space belongs to the special class of spaces called Hilbert spaces. The inner product is not a simple thing to learn just from the definition. So let's see some examples. First, we are going to define the inner product in Euclidean space of dimensionality n. Let x and y be some vectors, and their components we denote by xi and yi respectively, where the small index defines the position of the vector component in the vector column representation. And we remember that for an Euclidean space, these components are just real numbers. Then we can define the inner product as this sum. We multiply the corresponding components of these two vectors and then add up all these multiplication results. The result of this operation is indeed a number or a scalar. Let's check if all the demands for the inner product defined like this are met. First, the conjugate symmetry becomes just a symmetry. As for a real number, its conjugate is just itself. And this demand is met. The linearity by the second argument is also satisfied, and even more. In Euclidean spaces, we have the linearity of the dot product in the first argument also. And the positive definiteness is also satisfied, since in this case the inner product of a vector by itself is the sum of squares, which is always greater than 0. And it appears to be 0 only if all the squares are zeros, which is true only for the 0 vector. Good. This operation of components multiplication and then addition really defines an inner product. And for Euclidean spaces, it also has a geometrical interpretation. First, the inner product of a vector by itself equals the squared length of this vector. So we can normalize any vector just by dividing it by the root of its inner square. Second, if we calculate the dot product of two normalized vectors, the result equals to the cosine of the angle between them. And this allows us to perform a very simple orthogonality test. If the dot product of two vectors is 0, it means that the cosine of the angle between them is 0, and these vectors are mutually orthogonal. Good. Now it's time to define the inner product in a vector space over the complex numbers. We'll define it pretty much the same way. For two vectors, x and y, we multiply the corresponding components and then add up all the results. But now these components are complex numbers, and to satisfy the conjugate symmetry demand, we conjugate the components of the first vector in this sum. The operation defined like this also satisfies all the demands for the inner product. You can check it yourselves. The most important result of defining this operation in our vector space is the possibility to define the length of any vector and the angle between any two vectors. The length of vector x is by definition the square root of the dot product of x by itself. And the cosine of the angle between two vectors x and y is again, by definition, the absolute value of their inner product divided by their lengths. You can see that lengths and angles in vector spaces over the complex numbers are defined by analogy with that in Euclidean spaces. We like Euclidean spaces because they resemble us the three-dimensional space we live in. We can easily imagine a vector space with dimensionality up to 3. And we have a natural understanding what is an angle between two directions and what is length. We can't, however, at least with the same ease, imagine a vector space with dimensionality higher than 3. Or a vector space over the complex numbers. For these spaces, we no longer have a natural idea of an angle or a length. But we obtain this idea by generalization, and we define them via this concept of a dot product. One more thing to notice here is this absolute value. In the spaces over the real numbers, the result of inner product operation is always a real number. But for spaces over the complex numbers, inner product of two vectors can be a complex number. And for it to be a properly defined cosine of some angle, we decide to take the absolute value of it. The absolute value of a complex number is always real, and thus defines the cosine of some angle. Thus, the angles in Hilbert spaces in general are not defined in an intuitive way, since we can't easily imagine them, but in this strict mathematical way. And since the absolute values are always positive, we don't have negative cosines anymore, which means in a Hilbert space over the complex numbers, we don't have obtuse angles. Now, when we have such a great instrument of defining angles and length, we can do this even with the vector space of square integrable functions. If we define the inner product in this space, we could define such things as functions length or an angle between two functions. And we could say that some functions, f and g, are mutually orthogonal. And indeed, we can do this. The dot product of two square integrable complex valued functions is defined as an integral of their product over the whole space. And again, to satisfy the conjugate symmetry demand, the first function in this product is conjugated. Again, you can check that this operation meets all the demands for the dot product yourselves, or you can just believe me. Now at last, we can justify our previous talks about the orthonormal basis. The orthonormal basis consists of vectors which are all mutually orthogonal and have the unit length. And now when we have the notion of an angle and length properly defined, we can check if some basis is orthonormal. The inner square of every its element must be equal to 1, and the inner product of any two different elements must be 0. Now we know enough to approach the notion of a conjugate space.